So for project 2, what we have here is okay, so you see this directory, right? Structure kernel user makefile. So first of all, Mac users, you should go to makefile and edit it. So you will have to Mac users with new Apple chip, not using Intel chip. So because you're going to be using Ubuntu 22.04 for ARM64, like newer Mac users. So therefore you have to specify a different compiler and a different linker, not the default one. Yes, so otherwise, if you use Windows machine, like Linux machine, or older Macs, so you're gonna have x86-64 machine, so you're gonna leave things as is. So just one minor note here. So, so the way that it works, so you run it in a Linux machine, but in the Linux machine, what is that? Give me 1 second. Okay. But but in the Linux machine, what you need to do is effectively need to run another VM, so kind of nested VM. So for that purpose, we use QEMU. So this is when you do make test, it will execute QEMU. So QEMU allows to run x86, 64, even if you are just running on ARM64. So irrespective of the architecture, it should be able to run it. So the only difference is that for ARM64, we have to have a cross compiler. So this is why we specify the CC and LD differently. But other than this, you're going to have exactly the same way to run it, whether it's a newer Mac or x86 64 machine. But regardless of this, we execute the x86 64 instruction set, and this is how we set up the page table. So what else? So in this code, you can see that there is bootEFI. This is just a bootloader, so you don't need to worry about it. But the way that it works, it will execute in the kernel. So if you go to kernel.c, it effectively will transfer control to the kernel start. And in kernel start, you'll pass kernel stack, user stack. So those will be page size buffers. Then there will be frame buffer. Frame buffer is a special video RAM where we can draw pixels. And then we have user code. So user program is in a separate binary. So this kernel is one binary and the user is generated as a separate binary. And finally, there's a memory buffer where you create a page table, and memory size is the maximum size of that buffer. So I believe it's around 32 megabytes. So it should be more than enough to initialize your page table. So then it is doing some initialization related to system calls, because this already some system which supports system calls. So then it also allows you to, for its extra credit part, it allows you to have this to integrate malloc, and it creates a heap. So it's, for example, it will have memory plus kernel heap size. So and then effectively what you're gonna pass here, kernel init, user stack, ucode, memory plus heap size. So we're gonna skip that heap that is left for the extra credit, and memory size minus kernel heap size. And finally, jumps to the user program. So now the user program, let me actually briefly show it. So the user program is here. So there is there is user entry, which just, transfers to user start, and user C, user start. So it will start executing this program when you transfer control to the user program. And then it will do some checks about what's going on in your system, whether you set up the page table, whether you didn't set up the page table correctly. So, so for example, let me give you an example. If you didn't set up the last question, so use a space, by default, when it loads a page table, it will still mark page as a user space accessible. But so that we can still execute this user program, because otherwise we cannot execute this. But it won't give you points for that, right? So only if you do the last question, question 4, set up your user space correctly, then it will give you points for that question. So yeah, that's how it works. But user program is going to be executed regardless. So as like even if you didn't set up, it will set it up for you, but won't give any points. So that's the way it works. Yeah, so other than this, it will support system calls. Once assuming that you answer the question 2, you should be supporting system calls. And then it will check, okay, can you see any system calls here? Okay, and then page table, the third question. This is whether you initialize the kernel page table. So by default, there is already some page table there, of course, but you need to initialize your page table. And finally, the user space, which you also need to initialize. So the way that it works, it will check at every step what kind of questions you implemented. And, as I said, for the last one, you may, it will already kind of initialize user space, regardless whether you implemented it or not, because otherwise you cannot execute it. But it will only give you points if you implement question 4. So that's the way it works. So anyway, so whatever the message that you see, that comes from the user program. So whatever the message that with the points you see, it's from here. You are not allowed to modify this file though, right? So just remember, you're only allowed to modify kernel code. And in the kernel code, I mean, I can imagine there's probably a way to trick the operating system to still give you some points. I mean, but you don't do that, because we will still verify your code. So yeah, so you shouldn't be tricking the OS to give you points. So now in kernel directory, so by the way, if we look at the make file, we can see, and let me actually run make. So when I run make, it generates, so it compiles the system, and it generates 2 binaries, kernel and user. So, and then it eventually is going to generate minus.image. So this is just a virtual disk image that it loads from, and just that will put bootloader there. We can actually even see what's going on here. So in the image, it will put the bootloader, then it will put kernel and user program. And the bootloader will load both the kernel program as well as user program. Okay, so in the kernel directory, you have kernel code .c. So here you have to implement system call, right? So I think for the most part, I mean, I think it's not a difficult question, because for the most part, it's already implemented. So for example, there is assembly code that routes system calls, but you don't need to worry about this. So here you can assume that you already, there is a way that we set up a system call, such as, let me show you in the user program. Let me go back your user C. Yeah, so syscall1, right? So you can, so the first argument is the number of parameters that you pass. And it's also like, this is also reflected in 1, right? So if you have syscall2, it's going to be different. But we only use 1 argument. And this message is from user space. So we want to print this inside the kernel. So we pass this message through the system call. So that eventually gets routed here. Oh, I'm sorry. This one is actually, yeah. So give me 1 second. Yeah. So no, I apologize. So we have syscall 0, for example. This means, that means we have 0 arguments, and then it passes the system call ID. And that's a syscall1, it's means that we have one argument, and one is the system call ID. Okay, go ahead.
Why are we casting string to a long?
Yeah, so this is because it's kind of a generic function. It doesn't care whether you pass in a string or you pass in an integer. So it just supports, let's say, one argument. So if you look at this implementation, sorry, if you look at the implementation, include syscall h. So you can see what's going on here. So there is generic function syscall0, syscall1, and so on. So the first argument specifies the system call ID. So that's the system call ID. Remember that you may have a lot of system calls in the system. So the first argument that you pass is the system call ID. And then it passes the arguments. Argument, for example, if it's syscall1, it only has one argument. If it's syscall2, it's going to have two arguments. So those are just generic functions, which you basically can use for anything, right? So let's say you have a system call that accepts one argument, and we have this one string, right? So that's one possibility. Another possibility, we have one argument, but maybe it's some integer. That still syscall1 will work. So this is why we kind of cast a pointer to an integer. So as long as the integer is of the same size, and it's the same size, long as the same size as size of void star, right? So that's going to be 8 bytes. So we should be fine, because inside the kernel we can cast it back to the pointer. So as long as we, this is the way that it's implemented in most operating systems. So you want to provide just general mechanism, and then a specific system call will, will pass these arguments, and then inside the kernel you will already kind of transfer it back to the original arguments, whether it was a string or whatever it was. So it's just because we want to use those kind of templates for everything potentially in the system. So otherwise we would have to write this assembly code for every single system call. And let's say we have 300 system calls. That would be a lot, right? So we wrote this for, from syscall 0 to syscall 5, and that's it. And we can use it for anything pretty much. Okay, so here in user, we pass the first argument is the system call ID. So for example, it's 1, maybe in this one is 1024, but doesn't matter, right? So you only need to worry about system call ID 1. So you don't need to support any others. And then it has, okay, this message is from user space. So that's the argument that you pass, the first argument, the only argument that you have. So now inside the kernel, what do you have? You have this entry function. So it's already connected through the assembly code. I can actually even show that. Yeah, I think. But you don't need to worry. It's already connected here for the assembly code. You don't need to modify anything here. In fact, you are not allowed to modify this one, right? But so you have this kernel code where it connects syscall entry eventually. So that's the system call entry for any system call, no matter how many parameters you have. So this is why we have the argument n, and then from A1 to A5. So that means we have up to 5 arguments in this implementation. It's kind of, again, a generic entry. It's just a single entry point. So once you look at the ID, you should know which system call it is, how many arguments it has, and so on. So if, for example, if you call syscall1, then the remaining arguments will just contain some garbage, right? So that's like from 2 to 5, so you shouldn't be using them. Okay, and then here you have kernel init. So this is where you need to implement the page table. So the first question basically asks you to create an identity page table for first 4 GB of memory. So even though we use 1 GB, this is, by the way, is here. So we specify that we are using 1 GB of memory here, memory 1024. So, but even though we are using 1 GB of memory, we still want to map 4 GB of memory. So why is that? Well, the reason for that is because we are not just having the RAM in the system, right? I mean, it's not just RAM that we have to support, but typically in the physical address space, you have some other things like video RAM and like frame buffer. And frame buffer would typically reside somewhere between third and 4 GB, right? So by default. I mean, typically it's defined as special bias tables, but but we're not looking at them. We just assume it's somewhere in 3 to 4 GB. Yeah. So and yeah, this is why you need to have entire 4 GB. So that means some of these mappings will refer to non-existent memory, and that's fine as long as you are not touching this memory. It should be okay. Yeah, but still create a mapping for the first 4 GB. Then the last question asks you to create a mapping for user program. So here you want to be careful when you create user code and user stack. Why is that? So for user code and user stack, let me just remind you one thing. Use this camera. Oh, not this one. Okay. Yeah, there is the computer itself has multiple cameras. Okay. So what we have is so let's say you have a page table here. You created a mapping, kernel space. Remember, this is level 4. So you created the kernel space mapping, like level 3, that we discussed already. So then I'm asking you in the last entry of PML4 to create a user mapping. So that's no longer going to be an identity mapping. That's going to be some different mapping. So in 511 entry, this was 0. This is 511. That will be the user mapping. And in the user mapping, you're of course going to create your own level 3. And I'm also asking you to use the last level. So again, you're going to have level 2 and so on. So just again, use the last level, maybe except the last page, level 1. This is where I say you can use anything here in level 1. So that's up to you. So the program is compiled in such a way that it doesn't matter where you're going to run it. So as long as as long as there is a page map there, it should be able to run. So this is level 1. Again, this levels are entirely separate from this level. So remember that. So this is separate pages. So in the user program, recall that somewhere in the middle here, we have a big gap, right? So this is 0 to 255, 256, to 511. Why is that? Because we assign extended the address. So that means the 47 bit, so the address is 47 bit is sign extended. It was 0, it will be sign extended 0, 0, 0, 0. If it was 1, it will be sign extended 1, 1, 1 in the upper bits, in the 64-bit address. So that means when you deal with 64-bit, when you convert it to 64-bit address, which you have to because your pointers are 64-bit, you have to be careful with what this address is. So my suggestion is to kind of go do it backwards, right? So for this one, it's easy, right? So it's we didn't reach 0 yet, so it's kind of the same as 0 extension, right? For the kernel space. For the user space, I kind of suggest you to do backwards. So count it from the end of the memory. So, for example, you can say, what is my what would be the address of this page, of the very last entry in this of level 1. So assuming I have last entry here, last entry here, last entry here, last entry here, what would be the address of that? Okay, go ahead.
Would it be all Fs?
But the page address should be page aligned. So should it be 2 to the power 64 minus 4 kilobyte effectively, right? Right? So minus 4096. So that's going to be the address of, you know, well, the beginning of that page, right? So once you have something in that page, maybe you have last byte, that's indeed going to be all Fs, if it's like last byte. But it starts at this address, the page, right? So you definitely don't have 2 to the power 64, because the maximum number you can present 2 to the power 64 minus 1 in the integer. So what can you do? Just curious. Well, one possibility is that you write this like this is all Fs, because you said that's going to be like all Fs in hex, like make sure you count correct number of Fs. Then we put ULL, like, oh sorry, unsigned lon at the end. Don't forget to put unsigned lon, because by default integer is only 32-bit integer. So you want to specify that unsigned lon at the end. But then you can say, okay, then I should maybe subtract 4095 rather than 4096, right? That's one possibility. Or another possibility is that 2 to the power 64 can be just 0 effectively, because at that point it kind of overflows and goes back to 0. So effectively have 0 minus 4096 or minus 4096. Again, use lon here when you represent it. Don't forget to specify lon, that it's lon. Because 2 to the power 64 is effectively 0. That's kind of an overflow at that point. And then you can go back. So basically you have underflow by subtracting 4096. So that way it will still work. So just kind of letting you know how to handle this corner case. Or don't use that address. Maybe you use some other address, but just, you know, because you're allowed to use anything in level 1. But just calculate it backwards. So I suggest that you calculate it backwards. So what is the total size of this? This is 2 megabyte. So that means this page is going to be, the start of this page is going to be 2. This is the last page. But the first page is going to be 2 to the power 64 minus 2048 multiplied by 1024. So that's the first page in level 1. Because it's 2 megabyte, 512 by 4 kilobyte, that's going to be 2 megabyte. So you like this entry more, just subtract this. You like that entry more, subtract this. a little bit, be a little bit careful on the corner case though, right? On the last one, because it may not be the best choice. Because there is easy to kind of confuse it with zero, and especially at the end of this page. So it's a little bit tricky. So typically you don't use first and last page in real life, because the first page is typically null pointer, and the last page is also reserved, typically the same for the same reason. So yeah, so I mean, first page, I'm talking about the first page here, in the very first page in the memory address space. But yeah, anyway, that you don't have to treat null specially, just mention in this. Okay, so just do it backwards, and you can compare that. So don't calculate it from here, because otherwise you have a 48-bit address which you may have forgotten to sign extend. So this is why it's like a very big address, because there's going to be 111 in front. Not something that, not zeros anymore, right? So you make sure that once we go through this boundary, this bit is going to flip from 0 to 1. So once we go from 255 to 256, this bit's gonna flip, and that means we have a gigantic jump. So we have zeros there before, now we have ones, because it's a sign extended. So it's like a huge gap between 255 and 256 in level 4. So effectively it's kind of divided into two pieces. But it's fine as long as you kind of keep kernel and user kind of separate. This is why we also split typically in OS kernel in x86-64 into two parts, kernel and user, so that they are in different places. So in real life, like Linux implementation, it's the opposite. So user typically goes here and kernel goes here. And then there is also some identity map, and that's a third map and somewhere in the kernel space. So what I did here in this was I combined kernel and identity mapping together and put it here, and the user is here. So it doesn't really matter. The CPU doesn't put these restrictions. It's up to us how we are using it. Okay.
When we go through and we initialize the level 4 page table, even though we're only using the first and last entries, do we have to create entries for every space in between?
Yeah, that's what I said last time. You have to initialize them with 0, because present bit for these pages should be set to 0. Otherwise, CPU will see some uninitialized bit and it will think that you are trying to request some unsupported features. Remember, some of these bits are reserved for future use. And if you have some garbage there, CPU will likely see that, and at some point there's a huge chance that some bit will point to this reserved bit, and the CPU will just crash. So it will say, I don't know what to do with this because I'm not supporting this. So it will not crash. It will probably generate an exception handler, but because we don't handle it in the system, it's effectively going to mean that it will crash. Okay, so don't forget to initialize everything. So everything should be always initialized. You shouldn't have any uninitialized fields. Every single bit should be initialized. So if it's not something that you use, it's a reserved bit, also initialize it to 0. Okay, does that make sense? So one more note here. So this is about stack and user program. So in the stack and user program, by the way, is it let me see if it records well. Yeah, I think it's almost fine. So in the stack and user program, so user program is straightforward. So user program, maybe you will select some page here. Let me put something in the middle as an example, right? You put user program here. So you create a mapping to the user program. So that means it has to point to the page where your program is. So initially, your program is initialized to some page where the user program is located. So now that page coincidentally is also a physical address, because remember that we created identity mapping initially. So virtual equals to physical. But now I'm asking to create a different mapping. So now it should be virtual to physical, but this virtual to physical should effectively, this virtual should point to this to the physical where the U program originally was initialized to. So, and after you initialize, you need to change your program. So after you initialize that, can see that user program. So U program is the buffer that we have, and that's going to be both physical, virtual, kernel virtual, as well as physical address. I'm saying kernel virtual because kernel will also have a map into that buffer, because we are mapping 4 gigabytes of RAM, and somewhere in the RAM it will appear, right? So this is where virtual and physical is the same. But here I'm asking you to initialize user underscore program to a different address. So U program was the physical address effectively, which was also the same as kernel virtual address. But now I'm asking to initialize a user virtual address and put it in user program. So in the comment I say it's okay to do for question 1, question 3, because when you load the page table, it will handle it automatically, but it won't give any points for that. If it sees that it matches the physical address, it will not, it will just not give the points for that. But it has to see that you have a separate mapping created for the user program. So this is what we're supposed to have, because initially we don't have any mapping for user program. So technically speaking, that would not even work if internally the program would not create a mapping for user program, even if you didn't implement it. But so you have to always create a mapping for the user program. The same as for stack, we have to create a user stack, and user stack has to be somewhere also here. So somewhere also here in level 1, you create a page for user stack. Again, for simplicity, we assume that user program is just one page and user stack is one page, just for simplicity. So now user stack is something a little trickier. Why is that? So any ideas why user stack is a little bit trickier than user program? So what's going on with stack? Where is it? What is the direction of the stack? How does it grow? So it goes to the opposite direction. User stack goes to the opposite direction. So in fact, in the PDF file, let me actually see that. Give me 1 second. In the PDF file, in the home, in the project, let's check that. So what do we have here? So it says here that in the last question. So yeah, please pay attention to here, right? So it first says that it first reiterates what I said, that from the bottom 2 megabytes, so just kind of count it backwards. So that way it's going to be easier for you, because this all F's is the last byte of that memory, because it's of sign extension. It then says, recall that the stack grows downwards. Thus the initial user stack address points to the next page. That means stack memory base plus 4096, because the user stack is 1 page. So that means user stack, ustack buffer. So ustack. So is it okay if I erase this? Okay. Okay, so what is going on in this user stack? So I should have problem like that. So we have this one in the stack. So what it says that user stack, and initially it's just use stack again, right? So use stack effectively points to the last. So basically, this is your page. Let's say this is the physical page. Physical page, not virtual. And it says that it actually points to plus 4096 to here. So this is where your stack points to. But that's the actual page that you are mapping. This is the beginning of this page. So what does it mean? What address do you need to map? So for program, it's easy. You need to map uProgram as a physical address. But what is the address here that you need to map? That's going to be, okay, go ahead.
When you say that we mapped U program, so we're given like the U program
Physical address,
right?
yes, which happen to be also the physical address, yes.
And we just map that to like the address field in the bitmap, like in that sample code that you showed us.
Well, when you initialize the page table, yes, so you have to initialize the for the question 4. I'm talking about question 4. So you have to map it somewhere over here, uProgram. And then user program should be initialized to the new address. So there are two variables, uProgram and user program. So user program should contain the virtual address, the final virtual address that's going to be used. So that's going to be virtual address. uProgram, for simplicity, you can just assume it's a physical address. Initially they're the same, as I said, until you implement question 4. So once you implement question 4, this is where you need to start worrying about user program and uProgram. Before this, you don't worry about this. Before question 1 to question 3, neither uStack and uProgram is nothing that you should be worrying about. But for question 4, this is where you need to change it. So now user program should contain the user virtual address, not the physical address. So because otherwise you will not get points for question 4. So it should contain the virtual address that you created in this mapping. It doesn't matter what address you choose. I'm giving you flexibility to choose in any of this last 2 megabyte range. As long as you initialize user program, it should be fine. So now for this one, it should be straightforward because uProgram already contains a physical address. Because this is the address that you just mapped here. So because you need to know the physical page number, you can specify it here. For user stack, on the other hand, it's a different story. For user stack, uStack contains physical address plus 4096. So that means to get the physical address, you have to subtract 4096. So you're subtracting 4096. Because it points effectively to the next page already. Because the stack grows downwards. So it goes in the opposite direction. So you first subtract from the address, then you place an entry. That's how stack works. So effectively, that points to the next page already. So and you have to get the original page because you want to map the original page, not the next page. So that's important. So that you subtract 4096 from uStack. So that's going to be your physical address. So now, what is gonna user stack contain? Because you also, so let's say you created this mapping, just like for user program, you created some mapping, but then eventually you have to initialize user underscore stack. And user underscore stack is going to be virtual address plus 4096 again. So that means the virtual address that you're going to get here, let's say, and then don't forget to add 4096 again. So effectively, I'm pointing to the next virtual page. So users underscore stack will always point to the next page. The question is what this page is. So initially it was the physical address that we added 4096. So to get the user stack, the real physical address, we have to subtract this. And when we create the virtual mapping, we have to also add it back, right? 4096. But that's going to be entirely different number now because that is different. This is like a very large number, right? Virtual address. So this is completely different address. So just don't get confused with this. So please read this carefully, this sentence, right? So recall that the stack grows downwards. So does the initial user stack address points to the next page? Stack memory base plus 4096. A stack memory base is the one that you want to map. Consequently, you need to get the physical page address correctly. That means subtract 4096 and map that physical address to the new virtual page, to the virtual address. Finally, the new virtual address that you will write to user stack should also point to the next virtual page. Now it's next virtual page. So that means you add 4096 back. So that's a little tricky, but not hard if you think why we are doing it. Because initially, so it always should point to the next page no matter what. And then the same picture you have here, just to so like what we discussed. So it's you can use any entry in level 1, but for level 3, level 2, use the last entry as well as for level 4 for user mapping. Any questions? So just make sure you read this again, because this is something that can be really error prone, right? And in fact, it may still run potentially because it just happened to have some page there, but it may create some invisible bugs when you sometimes crashes, sometimes it runs fine. So make sure you map user stack correctly. Okay, let's. So any other questions about project 2 so far? Yeah, I think it should be relatively easier. So some of you asked about memory allocator. What I mean, if you worked in a different group, what should you do, right, in terms of extra credit? So it doesn't matter which, you can use your code for memory allocator. You can use your partner's code for memory allocator, even if it came from a different group. But I mean, as long as it's either your code or your partner's code, but let's say previously you didn't work together. So that's totally fine. But so because but as long as this works, right, because it shouldn't crash. So here I'm not evaluating any performance of your memory allocator, so even a checkpoint version should be fine. So as long as it doesn't crash the system, it should be fine. And to be honest, as long as it doesn't crash the system right away, it should be fine. Yeah, so please use any code that reasonably works. So if your code was buggy, maybe you want to use your partner's code. So I'm not putting any restriction here, but of course you cannot use someone else's code. So please use either yours code or your partner's code. So if for whatever reason, you know, you were not able to finish project one for whatever reason, I don't know, you know, probably you still have some checkpoint or something like this, right? But even though, let's say, checkpoint was not working and you still want to get extra credit, I mean, maybe this is the time when you can implement at least the textbook version and or at least something simple, maybe even simpler than the textbook version, and integrate it as an extra credit. Okay. Yes, so let me, I don't know if it was, okay. Let me open today's slides. So we will cover some material that we didn't cover last time. So please start project 2 earlier, because don't put it off till the last moment. Because yeah, so because the problem with this, it's better, you know, it's better to finish everything early than to be late, right? So it's better to finish it maybe this even this week, and then have the next week doing something else, than, you know, trying to finish it in the last moment. So in fact, checkpoint, don't wait till the checkpoint due date. The checkpoint is just to make sure that you have system up and running. So you shouldn't be waiting till that deadlines. So, you know, please get started. I mean, once you submit the screenshot, you know, just work on the on like one, just work on the main part of the project. So last time we talked about system calls, we looked at the S trace, and then we came to the you know, to the part where when we were talking about threads. So that's something that we haven't started talking about yet. So the idea is that you know, so we can use so first of all, with respect to threads, what is thread fundamentally? Well, it's just some entity that allows you to execute part of your program, you know, like separately from another entity, right? So if you have multiple threads, you can execute one thread on one core, you can execute another thread on a different core, or you may be able to execute it on the same core. It doesn't really matter, right? So you can be time sharing the same core. So there's something that effectively runs in parallel or concurrently with another thread. So you split your program such that you can run those things in parallel. Now, unlike processes where we have a separate page table, for threads, we expect that we have the same address space. So that's like whatever resources we have, we should have the same kind of resources for every thread in the process. That's our high-level definition. So now let's look at more specific definition. So thread managed by POSIX threads library. This is libp thread. So it's kind of similar to libc. This is also like when we have libc library, but now it's specifically dedicated to thread-related things. And POSIX, by the way, if stands for the Portable Operating System Interface. So that's some standard that, at least aim to kind of create more or less compatible interface across different operating systems. Of course, that didn't fully happen, but still, to some extent, even Windows supports POSIX to some extent, not fully. So now the kernel, well, actually, maybe now these things are changing but anyway, yeah. So, this is at least something that you have, for example, in Linux, I guess, in Mac, they should support POSIX. So the kernel, that means Linux, in our case, uses different abstractions. Like it's not called threads or processes. So in fact, in terms of Linux, there is no fundamental difference between a process or a thread. Instead, it calls these things tasks. So whatever it is, whether it's a thread in one process or it's a thread in a different process, that's going to be counted as a separate task. So now, some tasks will have the some shared resources, such as shared page table. And they maybe have some, task group even or something like this. So this is maybe what will be corresponding to the process ID. So that you can think about this as a process ID. Just give me 1 second. But in terms of Linux, it doesn't matter. It's still a task. And now the question is how you map tasks to threads. So we will talk about this. So first of all, let's just look at how process address space works for one thread. So you have core, data, heap, and then maybe stack at the very end. So stack goes to the opposite direction. So this go from 0 to 2 power 64 minus 1, something like that. I mean, again, it just depends on architecture. Of course, in x86 64, we only have effectively 48-bit, not 64-bit, but it's kind of sign extended also. Yeah, so now for a process address space, when we have more than one thread, so we will have the same code, we will have the same data, we'll have the same heap. So those things are still going to be the same. But we will have separate stacks for each thread, and program counter for each thread is also going to be different. So the place where we are in the code right now, that's going to be different for every thread. So, but why do we need separate stacks? Any ideas? Why do we need separate stacks?
We have to save the register for each process.
Yeah, that's true. And because of also preemption, right? So because of preemption, we can preempt the thread at any point. That means whatever was stored on stack, we don't know at which point we stored that, and we cannot use that stack for a different thread. So stacks have to be different because stacks have this local, variable, temporary local variables that are for functions, for the current function that you're executing. So each process consists of one or more threads. That's a high-level definition. So the threads can be executed concurrently, but not isolated from other threads within this process. So the kernel defines tasks. So task, again, if you have the same page table, that means we're going to have the same code data and so on, right? And then we're going to just share the same page table across different tasks. And maybe another task it belongs to a different process, that's going to be a different page table there. So the OS scheduler will execute tasks. So it doesn't really care whether it's the same process, not the same process. It may actually do some optimization because definitely it's better to avoid switching page tables back and forth because it's going to be expensive. But other than this, it doesn't really matter from which task we are switching. So just to give you an idea what kind of models we can have. So the simplest model that you can have is this N to 1 model. That's one that is in the middle. That means multiple threads in the user space are going to be mapped to just one task in kernel space. This is sometimes also called the user space threading, right? So when you run thread library effectively, but the OS doesn't provide any special support for threads. That means you just fundamentally have just one task in the OS kernel that corresponds to this multiple threads. And that task can be scheduled by any of the CPUs if your operating supports multiple CPUs, multiple cores, or maybe it's just the same CPU, right, for everything. Now, this doesn't really allow true parallelism for different threads. Only one thread is active at the same time, right? So now the model that Linux uses is called the 1-to-1 model. So that means each thread corresponds to each task. That means all these tasks in the like all this control from the context switching is on the kernel's shoulder. So the kernel has to decide, okay, what task I need to schedule right now, and this task has a direct map into the user space thread. Whether it belongs to this process or to the other process doesn't really matter. So, and then the kernel decides, okay, maybe I'm going to schedule it on this CPU, maybe I'm going to schedule on the other CPU, can schedule multiple tasks on the same CPU and time share that. So that's up to the OS scheduler. So, and finally, there is kind of a hybrid model, also called M2N model. So this is something that you won't see frequently, but there is some, some variation of this. Sometimes people call fibers rather than threads, or something along the same lines. So the idea here is that multiple threads can correspond to the same task, but you at the same time can still have multiple tasks. So in typically M number of threads is going to be significantly higher than N number of tasks. But doesn't have to be one anymore, like we had in N-to-1 model. So number of tasks can also be, so you still have parallelism, in other words. So typically the way that it will work, you create number of tasks roughly corresponding to the number of CPUs that you have. And then, so that you will allow parallelism. And then in user space, you can still switch different threads on different tasks, right? So you can decide which task you're going to use. So effectively now you have two-level scheduling. One is happening in the operating system kernel itself, which schedules tasks on different CPUs. And then the second scheduler runs in the user space, so which decides which thread to schedule on each task. Because now the spread one can be scheduled on task 1 or maybe on task 2, that's up to the user program. So effectively tasks in this kind of scenario becomes some sort of virtual CPUs. From the user program perspective. So, what is the advantage of N-to-1 model? We said the disadvantage there is no parallelism, but there is still some advantage. So the advantage is that we can switch cheaply from one thread to another thread by doing it in user space. We don't need to have any system call. That is not the case in 1-to-1 model, where you have to have a system call to switch from one thread to another thread. So in M2N model, it kind of tries to reconcile both. So it allows parallelism, but at the same time allows cheap context switch from the user space. But the problem is that it has some other issues, because now we have two-level scheduling. This is why it's not necessarily that popular in Windows or Linux. But there is still some variations of this. Sometimes, as I said, called fibers, not threads. They would call, those final threads as fibers or something like that. Yeah. So let's stop here and let's continue next time.